Guys, don't disappear on me. Oops. Guys, don't disappear on me. Okay. Wow. Oh. All right. This is better. So guys, look at this number. The numbers when we didn't divide by 10, what were the numbers we were getting, more or less? 0.1, 0.37, 150, and 8. 0.1, 0.37. So now ask this question, guys. What do you see when you see these two arrays of numbers? Is the largest number still huge compared to the second largest number? It is not huge. Okay, I'll wait for people to come back to the coffee. What does that mean?
Probabilities are going to be somewhat distributed.
Yeah. So it means if you lay these numbers out and you divide a pie, a line with this will occupy this will occupy a little bit more. Like if you look at these numbers, half, and 1, let's say one unit here. This looks double of this, more or less, let's say about this much, right? And then the third one is this, 1.65 should be 3 times this, maybe this, okay. And then 1 unit. And then I should erase the rest of it. And the biggest one is here. Now, if I throw a dart, so, okay, I'll repeat what I said. When you take a much higher temperature and you make a line, you divide a line based on that temperature, do you realize that the biggest one is not occupying so much space? So if you randomly throw a dart at it, you realize that the most probable thing is not likely to be overwhelmingly preferred or picked up, isn't it? Do you see that? So then as you increase the temperature, what happens? The second most likely, third most likely, other words, they have a fair chance. Other tokens have a fair chance. Right? And so when you sample off a softmax with a temperature, what happens? The higher the temperature, the more likely you are to deviate from the most probable choice. Make sense? And that is why in an LLM, those of you who use that API, you must have noticed that if you set, actually there is a problem. They give you temperature. I'll use the word little t is equal to 0, and you can keep going on, right? And they advise you up to t is equal to 1 or 2 or something like that. Actually, their t is e to the temperature as we mean it is actually e to the power 0, e to the power 1 e square, right? So what is it? When you set the temperature to absolute 0, what does that mean? This is equal to 1, means you're not using temperature at all. The most likely thing is going to be preferred. When you set the temperature, by the time you set the temperature to 1, what does it become? Yeah, 2.7, right? 2.72, and then this becomes 8. So in other words, you're dampening it down. The spill, those things, the histogram is getting dampened down quite a bit. Right? That's it. So that is where the creativity of an LLM comes from. Are we getting that? Right? That's what you do. So
So the nearby words are getting more chances as well.
Yeah, the next likely words are getting more chances like that. And so when you do that, people often argue what is the correct temperature. You must have seen literally blogs written about, oh, pick this temperature or that temperature. In view of what you learned, what should the temperature be?
Depend on the use case.
It depends on the use case, exactly. Right? You should think about your use case. How much of predictability versus flexibility or creativity do you want in that? That should determine that. And then there are other factors which do a similar job. Like, for example, you can say top K means a pick from only the top 3-4 probable. You still use this probability thing, but pick from only those. Ignore the rest. If you happen to land on anything else, try again. Right? Or you can say P is equal to total cumulative probability is, let's say, 0.5. Means pick the most probable, the next probable, so long as the cumulative is up to 0.5, and then ignore the rest. So these are all ways of controlling the creativity of it. But you see, guys, how the so-called creativity of LLM, it ultimately has such a simple origin. Anyway, that was a huge digression. The only reason I brought it up is because our course is about LLMs. And now we'll get back to what we have. And then I hope as we read.
So notice that even if temperature is 0, sometimes it still changes.
Yes, it will.
So there must be some other parameters that are also controlled.
No, Prasanna, think about it. All I'm saying is, even when the temperature is 0, look at it. You are still sampling. Temperature 0 means that the highest probable item occupies a lot more space, but you are still sampling it. It doesn't guarantee at 0 temperature that the most probable thing will get picked. Right? Remember, sampling is happening, and sampling is what gives it the creativity.
We can't turn off sampling.
You
If
can't
we do that,
off.
then the LLMs don't work.
They just become very boring.
Yeah.
Terribly boring. Right? See, if you're doing a classification job with the encoder part of the transformer, like we were doing somewhere in this bootcamp, I hope we were doing at some point, forgotten. I'm pretty sure we were doing. But then you don't want sampling. You want to know which is it a cat or a dog? Right? You don't want to change the answer. Then you don't sample. But when you're in a generative mode, sampling, empirically we have found is a good thing. You want to keep certain stochastics there. There's a reason why we call these machines stochastic parrots. So far, so good. Okay, now we'll come back to the paper. Toxicity has nothing to do with it. That is entirely different. That depends upon the data it was trained in. Unfortunately, there is a lot of toxic content on the internet. See, guys, here's a fact. You say something really bland. For example, you say that, let's say something really bland. The auto-regressive models produce the next token by sampling off the softmax. Nobody will listen to it. Now you say, did you know OpenAI is using something called nucleus sampling? They're going nuclear on it, and it will destroy the world. They're producing text that will destroy the world. Now that thing will go viral. Let's just say, right? You make a conspiracy theory or something like that. And so the fact of life is, and there are enough studies on psychology that shows that we all go for the dramatic, right? If I tell you that the weather is beautiful out here, it's fine. If I were to just tell you that, hey, did you notice that it's fine here, but in the mountain up there, it's snowing. I don't know why. You will be incredulous, but you will walk out to check. So it is a clickbait, right? And the web is filled with junk, predominantly junk, because junk attracts human beings. And the whole monetization model is clickbaits.
Right? Tabloid newspaper is now public. Tabloid.
Yeah, exactly. Right. Right. So that's that. And so the models are inherently toxic. Remember, I was telling you that you start with a pre-trained model. What is it? It's deeply toxic. Oh, maybe I haven't got you in LLM2, we'll talk about it. A pre-trained model is toxic, it's uncensored, it will spew out hate speech. Because that's what a lot of the web is noted for. But then you go through supervised fine-tuning and reinforcement learning and alignment with human preferences. And then you create something that is less of a monster. I would like to show you a picture actually, which is actually from the second part of this course. Since you brought this up, but it's a huge digression from what we're doing. I'll do that anyway. Just give me a sec. But toxicity is an entirely different question. Let's go to LLM fine-tuning. Where is fine-tuning? Okay. Maybe, why do we need to fine-tune models? I have a picture here that sort of speaks for itself. Oh, where did my picture go? Oh, here we go. We are getting to that. Somewhere here is a picture. No. Okay. There we go. Instruct paper GPT. Okay, this is it. Look at this picture. Do you see this big monster? When you pre-train a large language model based on all the data, all of human knowledge, it is this big monster, multi-headed monster, right? In India, you would call it the Ravan, right? Yes. This is it. Then what you do is you do some supervised fine-tuning with data, and it begins to look like that pink guy, right? A bit of a tame monster, but still a monster. And then you go through some further human preference. Today we call it preferential optimization, human preferences. You can do it with, in this picture, you do it with RLHF because that's how initially the Instruct GPT paper did it. But today you can do direct preference optimizations, etc., etc. There are many ways of doing it. And then you create this cute little yellow thing. So when you talk to this cute little yellow thing, your chat GPTs and whatnot, you have to know that this is a child of this pink monster, and that pink monster is a child of this big multi-headed monster. So behind it all, there is still that big multi-headed monster there. Right?
Yeah. So another interesting question that I got is, so we talk about temperatures and everything. How does it relate to grounding? Is it grounding at all?
Forget it. Let's come to that later. Let's take that off. That will be too much of a digression at this moment. So guys, let's look at this. One more. The one point that I wanted to make is, so now you understand how it is. But in the loss function, the point that I want to make is, the loss function, unlike the way most of the code on the internet has implemented, not many people remember that if you look at the original loss function, do you notice that there is see, the typical loss function would be negative log likelihood, right? Log P. Remember, what is log P? Negative log likelihood. We talked about this. This is your loss, right? Yeah. Minimizing it. But for any given item, you would do this, PXI, I, typical negative log likelihood. But here they're doing something else. Do you notice there is this extra term here? Weighting. They're attaching a weight to it. What is this weight? They're making a very common sense statement. You would agree that, first of all, if the picture is mostly filled with sky and less with, let's say, a cat, then when you're training the model, you should give more weightage to getting the cat wrong. All right? Because you can easily miss the cat, the tiny little cat in the big picture. So the class weightage should be one factor. The other thing they do is they forget the exponentiation part. They also take in the distance factor into one. Now, what is these distances here? I'll give you the basic intuition. Distance to the border of the near. So suppose, think about it this way. You're doing segmentation. This is a cell. Suppose you are here, right? And would you agree? So suppose the cells are here. The nearest cell boundary is this. This is your distance, right? B1. Would you agree that the closer you are to the boundary, the more important it is to get that point right? Would you agree? And the further you are from the boundary, it's okay. Even if you get it wrong, doesn't matter. Because what are you trying to do in the masking process? You're trying to make this line right, yellow line right, isn't it? And so you should not give the loss or the mistake made on all points, treat them equally. You should give more weightage to mistakes made near the boundary. Does that make sense? So that is the first term. And the second term is they added also the distance to the next. So, they were playing with it and doing things, right? You can play your own games, but it also points to how researchers, they play these games to squeeze the last juice of accuracy out of your models, which is a fairly common technique, by the way. UNet, you will see many researchers will do small adaptations of these techniques to improve their loss function.
So exponentiating that.
Or exponentiating is simply to give it positive.
Make it bigger.
Yeah, no, positive. If you don't exponentiate it, remember e to the minus something, right? What is the shape of e to the minus something? E to the minus something looks like this. Minus e to the minus x square looks like this on both sides. But since x is positive, distances are positive, any d value will look like this. So what does it mean? The closer you are to the boundary, the more weightage to give, isn't it? But the further you are from the boundary, it doesn't. Ignore that loss term. What it does is, the terms, the little bit of mistakes that you make far off, in the blue sky, ignore it. Don't count it that much. But give far more importance to closer to the edges, the loss function. So that improves the model quite a bit. And it's a very common technique that researchers tend to use. Anyway, it was there in the original UNet paper. And it's one of the ironies that most of the time when people talk about UNet, they miss that subtlety. They don't realize that too is baked into it. So with that, I'll stop. I'll give you guys exactly 10 minutes break. And then we are going to do, in a marathon session, we have 2 hours. We are going to do 2 important papers, Detter and Sam. And if we can't do Sam now, we can do Sam next time. But we'll do Detter. So 10 minutes break, guys. Yeah. So guys, this was hardly a talk on UNet. It was a